Swayam Prabha. Digital India. Educated India.
Welcome back, students. So today we are going to talk about continuous bioreactors and their designing. So we have been able to now discuss about what are bioreactors. Then we also discussed the design of batch bioreactors. Then further we discussed the design of fed batch bioreactors and the application of fed batch cultivations in fermentation industry. And now today we are going to discuss about continuous fermentations, their applications, and then design of a continuous bioreactor. So what is an ideal CSTR? So you must have heard the term a lot of time, CSTR. So this CSTR stands for continuous stirred tank reactor. Now in ideal CSTR, we say ideal because it is a perfectly mixed stirred tank or mixed bioreactor. Now ideal CSTR, we can assume that the microbial population is being maintained in a state of exponential growth over a very long period of time. Now continuous cultures, they can be operated either as chemostat or as a turbidostat. What does chemostat mean? The flow rate is fixed and the rate of growth of the culture is being adjusted to the flow rate. So this gives us an opportunity to manipulate the growth rate of the culture as per the modulations in the flow rates. Turbidostat. Now in a turbidostat, the turbidity inside the medium is set at a constant value. How? This is done by adjusting the flow rate. So the flow rate is no more constant. We have to keep changing and adjusting the flow rate so as to keep the turbidity at the constant level inside the reactor. This is more difficult to operate than a chemostat because then you need an inline device which can continuously monitor the turbidity, and we also need to ensure that the pumps are calibrated properly and they are functioning all throughout the fermentation process properly, because the flow rates will have to be manipulated in order to keep the turbidity constant. So it is much easier to run a chemostat because turbidostat would require an optical sensing device and a controller to control the flow rates. Turbidostat is however recommended when CSTR is to be operated at high dilution rates and therefore can prevent washouts. We will see what is a washout phenomena and then we can come back to this point, that how a turbidostat can be more useful when the reactor is to be run at very high dilution rates where the risk of washout is very high. Washout means the cells getting washed away from the reactor in the outlet stream. So this is a simple schematic of a chemostat and a turbidostat. So as I said earlier, if you see the chemostat given on the top, here the volume will remain constant, shown by the dotted line. It is not changing, and here in a turbidostat there is a controller which controls the flow rate of the pump or the calibration of the pump, and there is an optical sensing device which will continuously monitor the turbidity inside the reactor or the broth. So the culture volume can be kept constant by an over harvesting device, So, there we need to ensure but that the turbidity inside the reactor, which is related to the cell density, is constant by maintaining the or by adjusting the flow rate inside the system. So, let us note down some of the notations which will be used when we will be designing continuous stirred tank reactors. If you can see the schematic on the screen, there is an inlet stream showing F as the volumetric flow rate of the feed, S naught as the feed substrate concentration and X naught as the biomass concentration present in the feed coming inside the reactor. The volume of the reactor is VR and the outlet stream has the flow rate F, substrate concentration S and X. Now, it is an ideal CSTR and running as a chemostat. So, which means that what is coming out, what we are measuring in the outlet streams, the variables, their values will be the same inside the reactor. So, O denotes the inlet conditions of the subscript, S is the growth limiting substrate. So, we know now the dilution rate is F by V. So, here because the volume is VR, so the dilution rate can be given as F by VR, which is an inverse of the residence time of the reactor. Now, continuous reactor operations, they are generally like in case of fed batch, they are started as batch, and if the purpose is to continue the growth phase, continue the culture to remain in the exponential phase to avoid nutrient limitation, then it is switched to continuous mode when the cells reach the exponential phase. Now, ideal chemostat, as I was mentioning, if we do a mass balance across this ideal chemostat for the biomass and apply, so if we do a mass balance, which means if we apply the continuity equation, the rate of accumulation of the biomass will be equal to the rate at which the cell is coming inside the reactor minus the rate at which the cell mass is going outside the reactor plus the rate of cell growth. And obviously, we are assuming, and obviously there is no, under all practical conditions, there is no consumption of biomass taking place. So, if we expand now, accumulation rate is being represented. So, now again in a chemostat, the volume of the reactor is fixed because the inlet and the outlet flow rates are constant at F. So, your X is the biomass concentration. So, it is a mass balance, but now the volume being fixed has been taken out. So, we can represent it as VR times dx by dt. This is the rate at which the biomass is coming inside the reactor. This is the rate at which the biomass is leaving the reactor, and this is the rate at which the biomass is growing, specific growth rate, growing inside the reactor or increasing inside the reactor, the growth is happening. Now, assuming that it is a sterile feed, so there is no biomass in the inlet stream. So, this term goes to 0, and assuming it is a chemostat, which means this continuous bioreactor is running at steady state. So, there is no net accumulation of biomass, which means there is no change in the biomass concentration with time in the reactor. So, if we do the rearrangement, again x and x gets cancelled, and you will see that as in case of quasi steady state of fed batch reactors, in continuous bioreactors running as chemostats or at steady state, your specific growth rate becomes equal to the dilution rate. Now, I hope you can understand the advantage of running a continuous reactor, which I just mentioned few slides back, that there is an opportunity to control the growth rate of the culture by manipulating the flow rate, because D is a function of flow rate. Now, the above equation, therefore, we are able to prove at a steady state the specific growth rate of the culture becomes equal to the dilution rate. So, because now the specific growth rate of the culture can be controlled by manipulating the dilution rates, the residence times can be used, or the dilution rates can be used to compare the effectiveness of the fermenters, which means what? For maximum productivities, shorter the residence time to reach the desired cell mass concentration, though more effective will be the fermenter, right. Let us see how to calculate the steady state substrate concentration. So, now we have understood how the growth rate will be related with the dilution rate. Now, let us see how can we find out the substrate concentrations, steady state substrate concentration or the product concentration and corresponding productivity of biomass and product. Now, we know at steady state D is equals to mu. If this culture is following Monod's model, again substituting Monod's model and rearranging, now D is the inverse of the residence time. So, if you now use this equation, do the rearrangement to find how CS is related to the residence time, you will find that it becomes equal to Ks divided by residence time multiplied by mu max, which is mu m minus 1. Now, this demonstrates what? This is valid only when the denominator, which is tau mu max minus 1, is greater than 0. Less than 0 it becomes negative. So, it has no physical significance, meaning. So, this in turn means that tau mu max has to be greater than 1. So, if we again bring tau as an inverse of dilution rate, so mu max has to be greater than the dilution rate for substrate concentration to have any valid numeral value. If suppose this becomes less than 0, then what happens? Less than 1. So, let us see, if your dilution rate becomes greater than mu max, what will happen? If your dilution rate greater than mu max, which means your tau mu max is less than 1. Isn't it? Tau times mu max is less than 1. This effectively means that the growth rate of the cells is now less than the rate at which the cells are leaving the outlet stream, isn't it? This would mean effectively that it will lead to the complete washout of the cells from the reactor. So, this is what is washout phenomena. When the dilution rate becomes greater than the maximum specific growth rate of the culture, beyond which the culture cannot grow, then the rate at which the cells are leaving the reactor becomes more than the rate at which the cells are growing inside the reactor or getting accumulated inside the reactor. So, this can lead to the complete washout of the cells. So, there will be no cells remaining inside the reactor. Hence, this will lead to complete washout, and this is called as washout phenomena. So, this is the condition which has to be followed to prevent washout, that tau mu max should be greater than 1. Now, for continuous reactors, for a sterile steam, your biomass can be a function of Yx by S multiplied by, this is the feed concentration and this is the concentration in the outlet stream. Now, assuming that Yx by S is constant, which is its theoretical value with no endogenous metabolism, which means, so then your biomass concentration at steady state in the outlet stream can be calculated in terms of the steady state substrate concentration in the outlet stream, which we just found above in equation 2. So, if you substitute this equation, let me make it a little clear. So, if you substitute Cs from here in this as given here, then you will end up here. So, this is how your steady state biomass concentration can be obtained if you know the dilution rate at which the continuous reactor is running and knowing the inlet feed stream and the culture kinetic constants. Now, how to determine the steady state product concentration? Again, we will make use of the yield coefficient. Yp by S is nothing but Csi minus Cs, which is equals to Cp minus Cpi. Cpi is the initial product concentration, initial in the sense in the inlet stream. Now, inlet stream again there is no product. So, your product concentration can be written as, let me read it again. So, your steady state substrate concentration has been substituted like above. Then you can calculate the value of product concentration. So, the microbial population density, it remains unaffected over a wide range of dilution rates. So, if you see the plot given here, x axis shows the dilution rate, your orange plot is the cell mass density. So, if you see as the dilution rate is changing, there is a very little change in the cell mass density, where with increasing dilution rates the cell mass density reaches to a point where after beyond a certain point of the dilution rate suddenly it starts decreasing. So, which shows that at very high dilution rates the washout has started happening, because of which the cell mass starts decreasing inside the reactor. Similarly, at very low dilution rates here, again the nutrient supply becomes limited and therefore the biomass concentration is less. As the dilution rate increases, the concentration of the nutrients increases, resulting in higher cell density, and then over a wide range there is not much significant change before the washout happens.